URLs. I've got truncated a little. Okay. All right. And today it's my great pleasure to introduce Professor Angelos Karametis from the Department of Computer Science at Columbia University. Angelos is a assistant professor of computer science at Columbia, and he received his master's and PhD from the University of Pennsylvania and his bachelor's degree from the University of Crete in Greece. His research interests include network and system survivability, authorization and access control, and large-scale system security. In a previous life, Angelos had enough time to contribute code to the OpenBSD project. So without further ado, Angelos.
I would have thank you. I would have spiced it up if I knew you were going to actually read that. But anyway, this will do. So thank you for coming at this fairly late hour during the day. And what I'm going to talk about today is some initial steps in our work to create self-healing software. And by self-healing, I mean a very ambitious vision of software that can identify failures of many different kinds and automatically take steps to correct them. So if you were here for the whole story of copying files back and forth, you know, that ideally 20 years from now when we solve all the problems, I'd like the system to figure out what it is that I want to do and do it, but we're a long ways from that. So the summary of the talk, and you have to forgive me for the slides not quite fitting here, but that was the problem that we're trying to deal with, was that we're trying basically to create software systems that heal themselves against failures, whether they are security attacks, whether they're bugs due to program mistakes, with as little or no, ideally, human interaction. So if you're going to fall asleep for the rest of the talk, that's the message I want you to take away, that, you know, especially if you fall asleep, that these guys at Columbia really solved this problem. You know, if you're awake, then, okay, you get to hear what we actually did. And so in doing so, we're really motivated by the current situation in the realm of software security, where basically the attackers hold all the advantages, which is they have the advantage of selecting the place and the time to strike, which is the traditional advantage in all conflicts in history. The attacker gets to choose where and when to attack, well, mostly where, when. And also they get to exploit large numbers of compromised systems to further enhance their attacks. And also, to a large extent, they exploit the fact that we all run the same version of the same operating system, or a fairly small number of operating systems and applications. And so all they have to do is find one vulnerability, and then they can write code that helps them automatically exploit that vulnerability in many millions of instances of that same piece of software, whereas we, the good guys, to the extent that we are the good guys, can't really or haven't figured out yet how to exploit automation to our benefit, at least to the same extent. Of course, this vision is very, very ambitious, and it raises several questions on whether it's even possible. And even if it is, in principle, feasible, whether it's practical, and then what are the trade-offs? Because as everything in computer science, we're giving away something in return for something else, right? Computer science all about engineering, making it somebody else's problem or hiding the problem somewhere else. Now, although I come from a security background, my and the work, and some of the work specifically I'm going to talk about here, focuses on a very security-specific set of concerns. In fact, the scope of the project is much bigger than just security, as I said earlier. We really are trying to enable software to deal with all kinds of failures. And for now, I'm going to define failures are very low-level software faults, which when you see them, you know they happen. So when your Internet Explorer crashes, you know that something bad happened, right? So you don't really, intuitively, you understand that this is a fault. So that's the kind of failure that we're going to be looking at. And then towards the end, I'm going to give you some sort of blue sky thoughts as to where we can go with this. And remember, the focus is always on software, in contrast with other work in this area of autonomic computing, as it's called, that tries to abstract away system components as black boxes and then try to move them around or reconfigure them and so on. We really are trying to peek into the software that somebody else wrote. All right, so the overview of this talk is I'm going to start by scaring you witless with the state of software security by citing some statistics from CERT and other agencies, other acronyms. And then I'm going to give a very quick overview of related work, what's happening in trying to protect against various types of software vulnerabilities and software-based attacks. And then I'm going to present the motivation for our work, self-healing software. What do I really mean by this? And two particular techniques that we developed that enable us to address a large class of software failures, and those are called microspeculation and error virtualization, very catchy names. And then I'm going to talk about how we use those two techniques in two specific systems, the worm vaccine architecture, which as the name implies, is aimed at dealing with the problem of network worms specifically, and then the STEM system that's addressed at a larger class of software type of faults. And finally, if I have time, I'm going to talk a little bit about this new concept we've started working on, which is application communities. All right. And at any time, feel free to interrupt and ask questions. I may not answer them, but feel free to ask them anyway. So what's the state of the union? Basically, you don't need me to tell you that we use a lot of software and increasing amounts of software, right? Every release of Microsoft Windows or any operating system or any application just adds more code. So not only we inherit all the previous problems that code had, we get the benefit of more places where failures might occur, and we depend on this software increasingly, right? So all sorts of systems are moving away from pure hardware and mechanical relays and things like that to fully automated software control infrastructures. Unfortunately, even though we depend more and more on software and computing artifacts, the quality of the systems, and particularly the quality of the code, hasn't really improved as much or at all for that matter. So what that means is that we open ourselves increasingly to being vulnerable to more software vulnerabilities, more software failures, whether they are accidental failures, program just crashed because the programmer didn't know what they were doing, or there was some kind of logical flaw that an attacker managed to exploit. So very, very brief example of what I mean, the kind of failure that I mean, buffer overflow attacks. It's probably beaten to death, but I'm going to very, very quickly go over it because the example I'm going to use it later. So you have the code on the left, which is this hypothetical routine that has this array called overflowed that hints as to what might happen to it later on, statically defined fixed size, and then we use it unsafely to copy one string to this array. And what might happen here is on the top is the program stack. This is the standard model of an operating system, what a process looks like in its private address space, right? The program stack grows lower, and what happens when the caller, in fact, is on the stack, sorry about that, when the caller is on the stack, we have the stack frame for the caller that identifies where the caller needs to return, where the caller needs to return when that code finishes executing, where the return value needs to be placed, all the arguments, so overflow is going to be over there, and so on and so forth. And when it calls string copy, there's going to be another stack frame that's going to point to the corresponding information for string copy. Now, what the buffer overflow does is, because string copy in particular doesn't check that the input, the source buffer matches is at most as big as the destination buffer, what might happen is string copy might continue overwriting past the end of the buffer and start overwriting control information that's on the stack. In particular, in this case, the return value, and more importantly, the return address. So that means when string copy gets to return, it's going to use information that was in fact contained on the source buffer. So if that is some kind of input that was received, for example, over the network, or that an attacker, a malicious entity, somehow provided, then what the attacker managed to do was overwrite control information that is used internally by the control logic of the program. And thus, the program gets to jump to a location that the attacker controls. So that location can, in fact, be part of the input, and that input can contain instructions that are executable in that architecture, and thus the attacker gets to run their own piece of code. Once they manage to do that, they're home free. Basically, they get to compromise that particular process. They run with the same privileges as the process. They can download more code. They can do anything they want. Right? So this is the very basic idea of sort of the first instance, not the first, the most basic instance of a buffer overflow attack. The only reason I mention it here is just to give you an idea of the kind of failures we're talking about here. All right. So what happens is that, in fact, these types of vulnerabilities are found increasingly in modern software. So this is data provided by US CERT, which is an organization that keeps track of vulnerabilities, attacks, and so on and so forth. And they only published this data as of the end of the third quarter of 2004. After that, they got too depressed and stopped publishing it. They said, okay, we're not going to publish this. So this tracks the number of vulnerabilities of distinct vulnerabilities that were found in different software packages, whether open source or Microsoft and so on. So, they peaked in 2002 at about a little over 4,000 different vulnerabilities. And then they went down a little in 2003, 2004, unclear. Remember, this is up till including third quarter of 2004. Likewise, the number of serious vulnerabilities that were discovered, that again, CERT post an advisory saying, hey, you really need to pay attention, has increased quite a bit since 2000, and shows no signs of coming down. Monitoring the relevant mailing lists also, sort of empirical evidence shows that those numbers are still at the same level. And the actual incidents are going up. We don't know about 2004, they stopped publishing. Now, these numbers have to be taken with a grain of salt because there really is no difference from the point of view of counting at CERT between an attack against a bank, a financial institution with 100,000 machines, that's one incident, versus one attack against my laptop. Right? They're fundamentally different types of incidents, but they count them as equivalent incidents. But anyway, that should give you some idea. And what's interesting is that many of these, and in particular many of the problems that are remotely exploitable, are software-based vulnerabilities of the kind that the example that I gave you earlier, stack smashing attacks, buffer overflows, and other variants. So in particular in 2003, 24, 25, depends how you count them, of the 28 remotely exploitable vulnerabilities were of the particular buffer overflow kind, and then 2004 similar statistics for the first 3 quarters. Interestingly enough, the pace at which these attacks arrive has also increased quite a bit. Symantec compiles a inventory or a report every, I think every half year, every 6 months, publishing the state of security or incidents as they see them. They have a lot of monitoring posts around the internet and look at incidents and attacks and probes. So they found that on average there were about 10 new vulnerabilities disclosed publicly per day in the first half of 2005, and there were 7 a day in 2004, just for comparison. The average time it took for an attacker to create an exploit that took advantage of a particular vulnerability was 6 days after a vulnerability was announced. So a vulnerability could have been announced by Microsoft saying, hey, we've released a new security update, so please download it. And on average, within 6 days of that, an attack would appear that would have reverse engineered the patch and created a script that anybody could run and compromise machines that weren't in fact patched. Now, I keep beating on Microsoft, but open source software is in the same sort of boat. It's not appreciably better. And again, 2004 similar numbers, 5.8 days. Interesting sort of outliers in this space. The Witty worm, which appeared middle of 2004, I think, appeared less than 48 hours before the vulnerability announced. The way some people counted it was less than 24 hours, in fact. And MyDoom may have been the first zero-day worm. That is a worm that appeared without any warning whatsoever. We didn't even know there was a vulnerability in a particular piece of software. There was no patch out that Microsoft had posted that people could, in principle, download, but instead the worm appeared, and that was the first warning we got that that piece of software was vulnerable. So clearly, there's very little you can do to react to such a problem, at least with traditional methods of waiting for Microsoft to post a patch. So what are the countermeasures? I'll go over them. Take this very quickly. Take this very simple model of a network. You have an attacker on the upper side and a defender on the lower side. So there are various places in this simple model where different kinds of defenses may be placed, and I basically categorize them in 5 different spaces. The first is beat on the software vendors to produce better software, right? So this is, okay, let's step out of the box. Let's go to the people that create the buggy software that we run and get them to train their programmers or to use better tools or better testing techniques, whatever it is, better quality control, and give us better software. That works to some extent. Microsoft, for example, has gone through quite a bit of effort to train the programmers, but we still have problems, and we know that that can only go so far. It doesn't mean we shouldn't do it, but it's one approach within the space of solutions. Another approach is network-based protection. So we put firewalls, whether inside the core of the network operated by ISPs or near the defending side, where we do things like filtering or signature based filtering or anomaly detection, things like that. So these work to some extent. They work against some types of attacks, not very well against things that exploit software specifically, and certainly not very well against, at least so far, against attacks that that we haven't seen before. They may work reasonably well if once we have a signature of an attack. We then may have host-based protection, that is things that we push on the software, and these may include things like hardware facilities, like the no-execute bit on some of the recent Athlons and Opterons, or I forget what they're called, the 64-bit architecture from AMD and Intel. Although even those, there was recently a paper that showed how those can be bypassed. So no panacea. Things like managed code, where the code operates under the auspices of some kind of security policy, and we monitor that. We've defined that security policy in terms of the interaction of that code with the rest of the machine. So that might not prevent the process from being compromised, but at least it prevents it from, it prevents an attacker from compromising the rest of the machine. Or things like compartmentalization. You run your web server in one virtual machine, your web browser in another virtual machine, and so on. Again, same idea. Somebody breaks in, at least they can't compromise the rest of the machine. We may have containment, which is in some sense, the logical complement of network-based protection, which is try to push the protection near the attacker. And the idea here is that when somebody attacks a machine, they take it over and then they use it as a springboard to attack other systems. So if we can detect that the machine has been compromised, perhaps as it's been compromised or because of its behavior after it has been compromised, for example, outgoing TCP connections from a web server, there really isn't any good reason why that should be happening. So then we can use containment or quarantining to isolate that machine from the network until the administrator has a chance to come around and fix it. And this is one of the approaches that Cisco's self-healing networks, or whatever it's called these days, that's one of the mechanisms that's used there. And finally, we can have software-based protection, which means now go into the particular software that's running on the machine, and rather than build things around it, go inside it and put barriers and protective measures inside it. So there are many different kinds of mechanisms that offer different trade-offs in terms of performance, a need to access the source code, and effectiveness in stopping the attack and perhaps maintaining the service availability. And depending on what you want to do, you use one or the other. So there are mechanisms that are very lightweight in terms of their performance impact on the service, but on the other hand, they catch a very limited set of attacks. And when they do catch them, all they do is they terminate the program rather than let it get compromised. There are more powerful techniques that can, in fact, ensure that the program continues running, which is a very valuable thing if you're a broker financial services firm or an e-commerce site where you lose money if your web server isn't running, for example. But the flip side of having this assurance is that things may be running many, many times slower. Right? So it's a very unpalatable trade-off in many cases. And then there are other techniques like randomization of the source code, again, of the program rather. So if a program does get compromised, the injected code is going to be operating in a hostile environment, in a sense. It won't know how to access the services to interact with the environment that it needs to. So it's going to quickly cause the program to fail. Again, this works against some kinds of attacks, but it doesn't do much to keep the service running. So you need other infrastructure around it. And by far, perhaps the most commonly used technique is patch management, which is simply wait for the vendor to issue a patch, download it, maybe test it before you download it, and then hope that everything works. The problem with that approach is that there's a long cycle in patch management from the time a vulnerability is discovered by somebody, and then the vendor may be notified, if we're lucky, before an actual attack is created. Then programmers have to put on the task. They need to create the fix. They need to post the patch, and people need to download it. And the problem is exploits and vulnerabilities can be posted and used at any time in this cycle. And this cycle can take at least several days, typically several weeks, many times several months, sometimes years. Right? So when we're talking about attacks that appear within 6 days, depending on this cycle, is really not a good way of doing business. Worse yet, even if they did do things the right way, it turns out administrators are very reluctant to just blindly apply patches, mostly because they don't believe that they've been tested enough. So this shows the percentage of Apache web servers that were patched in response to a disclosed vulnerability to OpenSSL, a cryptographic library that's typically used by all Apache server implementations. So at day 0, none of them were vulnerable. I'm sorry, none of them were 100% were vulnerable. None of them were fixed. At time 0, the announcement and the patch were made available. Somebody said, "Hey, you need to fix it," and then some administrators actually fixed it. But basically, about 60% of all servers, a little over 60%, stayed vulnerable. Then a worm actually appeared that exploited this vulnerability. So you'd think, well, this is a sure sign, if I ever need to patch it, I'd better do it now because I'm going to get compromised. Well, it turns out the marginal sort of number of administrators was about 20%. So even long after a worm appeared, a clear exploit was out there. It was compromising machines, bringing them down. 40% of the servers remained unpatched. Some would say, well, the administrators were lazy, or they didn't know or didn't care. In reality, what happens is there's this trade-off between availability and security that many of these fixes and the patches encompass. So you have to decide whether you're going to patch your Apache web server, your IIS server, or whatever other service, and hope that it works, or you're going to delay until enough others have deployed it, and you've heard from the grapevine that, okay, it seems to work fairly well. Right? And in fact, that is what's happening. Administrators don't want to be the first ones to adopt a patch. They want to wait for others to be their guinea pigs. And there's good reason for that. Microsoft posted some, a while back, a researcher from Microsoft did some simple counting, and they found out that for every critical security patch that Microsoft issued the past 4 years, they often, in more than 50% of the time, they had to go back and reissue that patch. So it actually not only fixed the problem, but didn't create more problems. Right? In 50% of the time, their patch created more problems. The latest patch that Microsoft released on last Tuesday, in fact, created a new availability problem. It could cause systems to crash, some systems, depending on their configuration. Right? And Microsoft came out and said, oops, sorry, unroll it, or don't apply it yet unless you know what you're doing. And sometimes 10% or 5% of the cases, they actually had to issue it 3 times. So the administrators actually are perhaps to some extent justified in being a little reluctant in sort of being the first to patch. So why is it so difficult? There are two levels at which this can be explained. At the high level, basically, we're trying to play catch up. The attackers have all the time in the world to come up with their exploit, to create their worms, to set things up, and then boom, they hit. And they take full advantage of the speed of the networks and of the speed of the machines that we have and the monoculture, software monoculture that's out there. And we're left there sort of standing with a baseball bat, hoping that we swing it blindly in the dark and we hit something. It doesn't work very well. Humans aren't very good at that, swinging bats, as baseball shows. At the low level, finding software bugs proactively is very difficult. We know that it reduces to undecidability, basically, or the halting problem. Right? We can't do it. We can go to some ways towards it, but we can't deal with it. And the reason for that is we're asking, where is the bug in this program? So is there a way of formulating the question in a different way, such that we can bypass this undecidability problem? So an observation here is think about your complexity theory, what you've been taught there, and if you think about NP-hard problems, if you ask, what is the solution to this problem, it's very difficult. You have to do an exhaustive search. On the other hand, if I give you a solution, definition of NP-hard problem is that you can, in polynomial time, verify that it's actually a correct solution to that particular problem. So it turns out there's an analogy here. If an attacker tells us, or somebody tells us, hey, here's a vulnerability, and here's how to exploit it, you can just run the thing and test for yourself that, in fact, there is a vulnerability and it works as advertised. So the intuition here is, why should we do the hard work? Just let the attackers that have apparently all the time in the world do all the hard work of finding the bug and writing an exploit and trying to exploit it, and just catch them in the act of exploiting it. And that act is going to tell us all sorts of details about the particular vulnerability and perhaps guide us towards a solution. Now, when I say attacker here, I put this in an adversarial environment, but you can start thinking about, well, I can perhaps replicate the conditions that lead to a general fault, that lead to my web browser crashing, and if I do analysis on that under those conditions, perhaps I'll identify a fault. So we came up in this idea of self-healing systems, which is sort of what we'd like to achieve. And so at a very high level, we need to structure systems. Our position is we need to structure systems such that they have this closed feedback loop where you enable the system to self-monitor itself, the software, and then in response to anomalous events, such as an application crashing or a detected compromise of that software, there's a step of self-diagnosis, introspection. And that ideally would help us identify the fault, the nature of the fault, where it occurs, all the relevant parameters that allow an attacker to exploit it. And then there needs to be a component of the system that creates possible fixes. And those fixes may be completely generic, or they may be very specific to the particular vulnerability and even the particular parameters of the fault. And then the system needs to be able to test those candidate fixes and select the one that seems to be the most appropriate. And if that indeed can happen, we go ahead and deploy. So this is the satellite photo kind of view of what a self-healing, of how a self-healing system should behave without saying anything about what this system is or what it does, how it works. So another way of thinking about this is what the military calls the observe, orient, decide, act feedback loop, which is this idea that you build, again, a self-monitoring, or not self-monitoring, you build an infrastructure that allows you to operate very quickly in response to detected events. They put it in the context of detecting enemy movement or enemy action, and the idea is if you operate really quickly, faster than, as they call it, inside the opponent's reaction envelope, then you can outrun them, and not in the literal sense necessarily, but you can out-decide them, and then you're going to win. So there are several dimensions. So if we can do the same thing here, then we can outrun the attackers or even the accidental bugs. So there are many different dimensions of what this self-adaptation can look like. You can think of learning patterns of input that we then filter, and we stop at the boundary to the system, or we detect the system being compromised and we quarantine it, or we restart it if it fails, or we do all sorts of other types of reconfiguration. All these are within the scope of self-healing, self-adaptive systems. We decided to look at what I call structural modifications, which is break into the software. Instead of treat a piece of program as a black box inside which we have no knowledge, try to pry it open with automated tools and try to change it internally in response to detected faults. So the challenge here is, how do we find, in many of the faults that I gave examples of, it's fairly obvious detecting the fault is fairly obvious. If the process stops running, then, well, that's a fault. If it gets compromised and you've put the appropriate instrumentation, you can in fact detect that the buffer overflow is about to happen. There's a lot of work in the research literature that tries to do exactly this. So the challenge here is not so much the detection, at least for the kind of faults that I've talked about, but in finding a generic remediation strategy. What can you do that's going to be interesting, that's going to address a large class of these faults without having to go in and do sort of, if you see a string copy, convert it to a string end copy. If you see this, do that. This sort of template-based fixing, which isn't scalable at all. Oops, sorry about that. So what got us thinking here was this idea of speculative execution, which at a very high level includes you snapshot the program, means you snapshot the program state at some point in time when you know the program is in a good state. And then you execute the code, you let the web server handle a particular request, and if you notice that something bad happened, well, roll back. So pretend that the server didn't ever do anything, and then pretend that the request was never received, and let the server restore it back to the known good state and let it run. The problem with that is that this works only if the input that leads to that particular fault, whether it's an attack or an accidental failure, happens rarely, and it's not in your critical path. If your PowerPoint or your Word crashes every time you type I, well, it's not really, it doesn't do you any good if the system pretends that the I button doesn't exist. Just not a satisfactory answer. There's also all sorts of side effects that now the operating system needs to keep track of. So what if the server touched the file or sent the packet out in the network while it was doing this work, and now you need to restore it back to its pristine state? Well, what happened to these changes? Some of those you could potentially keep track of, like the file system, and unroll those changes, but only if other processes haven't already touched the same data, otherwise it becomes too complicated. The things that you send out on the network, well, there's no way to recall them, right? If you've said something, there's no way to unsay it. And generally, it's a very heavyweight mechanism for doing generic recovery of programs when we're worried about sort of perhaps frequently occurring events, such as an attack might be. So instead, what we do was came up with this technique that I call micro-speculation. And the idea there is, instead of treating the whole program as a black box and pretending and snapshotting that and recovering, instead treat just a piece of code that immediately contains the failure that you've noticed as a mini program that you need to snapshot and then recover from when that fails. So in particular, the granularity at which we decided to operate, and it will become clear in a second why, is a function, a code function, right? And rather than use speculation at all times, because we don't know whether an attack whether a failure might occur, instead or for the whole program, we identify the piece of code, the function that we need to speculatively execute based on previous observations of failure of that piece of code. So we wait until the program fails a couple of times. We find out that, well, it crashed when it was executing in this function. So now we're going to speculatively execute this function every time. All right. The nice thing about this is that there's very few state changes that we need to keep track of. And in particular, in many cases, you don't even need operating system support. I'll talk about two ways of implementing this trick. But if you do have operating system support, then you can speed it up quite a bit. And of course, when a fault occurs, whether it's an attack or the application crashes or anything that we define as a fault. And so far I've given examples, but I've left it unspecified as to what exactly a fault is. I'll keep it that way for a while longer. When a fault occurs, we undo the effects of the execution of that piece of code, and we take a different execution path. Well, okay, what kind of execution path could we take? So here's where the second technique comes in, which we call error virtualization. And the idea is, based on the function type, say it's a function that returns an integer or a pointer or what have you, pick a return value that would typically signify an error code for that function. So integer functions, by convention, most people write them such that a -1 or a 0 sometimes is an error. And a function that returns a pointer, typically an error is a null, right? So you can use such static heuristics. You can profile the application and find out what may be, or do static analysis of the code, or use hints of the programmer, and sort of guess with some confidence what may constitute valid error return values for a particular function. There may not be any, by the way. So now, when we unroll the execution of a piece of code, we pretend that this function returned one of these error codes by placing the appropriate value in the call stack and then returning control to the caller. And effectively what we're doing is we're catching a generic fault, like a buffer overflow or the application crashed because it dereferenced an illegal memory location, and we stop the program from doing that, from being subverted or crashing or whatever the effects of the fault are, and we convert this fault into an inline error code that we hope the caller is going to catch because the programmer wrote defensive enough code to catch some kind of error return from the callee, right? So this, as I say, smells a little like exception handling in Java perhaps or C++, except it's not quite the same because we don't require the programmer to have put this code in. In fact, we're trying to take advantage, to the extent that the programmer has done so, of the error handling code that is already in the program. So is that going to work? Yeah, right. So we ran a few experiments. We took Apache, SSH, dbind, and a couple of others I don't have here. We asked the questions, how many functions are important, which means how many functions could we cause to fail, and by using microspeculation and error virtualization, the program wouldn't be able to continue executing, right? So basically, we run standard benchmarks against some of these applications. We extracted the call graph, the actual functions that were active for the execution of these benchmarks, and then used fault injection against individual functions, one at a time. So in the case of Apache, there were 154 active functions against when using Apache Bench or Web Bench, I forget which one. And then we created 154 instances of Apache, in each of which one function would consistently fail every time that we used it, right? And we pretended that it failed with some error code that we guessed using static heuristics, just based on the type of the function. Nothing too fancy here. And we rerun the benchmark for each one of those. So it turns out that for 90% of the functions in Apache, you can do that, and Apache will keep running, will keep having the same behavior as it would have if the programmer had put code that said, oop, something bad happened here, and I'm going to recover from that. Surprisingly for Apache, in many of those cases, the web pages were actually served correctly. The benchmark completed correctly, right? Very surprising. Basically, we threw away code from Apache, and it still performed its task. That tells you there's a lot of redundant code in there. But it also tells us that there's a lot of code, or rather that programmers write defensive enough code, but don't catch all possible exceptions that may occur, right, such as buffer overflow. So if we can catch them somehow, and we can convert them into these inline error return codes, then there's a high probability that the program is going to behave correctly. Well, for some confidence of correctly. So now, of the 15 functions that caused the crash when we did this fault injection, 10 of them, in fact, were in the startup phase of the program. So in fact, we should discount them because we don't really care about failures that occur there. They're not affected directly by input from the network. So we'd never actually get to fix software in those cases, but it's a matter of semantics. For SSHD and bind, same type of statistics. Near 90% of the functions that were active, we could do fault injection, and the program would keep running and keep serving subsequent requests. Very surprising result. So again, this points back to this idea of well-behavedness of code, and that programmers may not be as incompetent as we've made them out to be. And there's some independent work that confirms this hypothesis that I won't go into due to time considerations. But there's some work at OSDI last year and at microarchitecture last year or the year before that shows that software is in fact quite a bit elastic. You can abuse it in certain directions along certain axes, and it'll behave in nice ways. But if you abuse it in different ways, it's going to crash. So getting back to how do we enable self-healing software, basically the idea is think of the previous sort of four-step feedback loop. Now what we need to do is put lightweight sensors around the software that we need to make self-healing. And then once we detect a failure, we need to have enough of a logic component that we can recognize the type of attack, which basically the sensor is going to tell us what it was, and also localize it in terms of where it happened in the code. And once that happens, we can use micro-speculation and error virtualization to apply a fix around that piece of code such that future instances of that failure in that piece of code are going to be treated according to what I've told you so far. And then this may lead to more than one possible fixes. And we can test each one of those and see whether they work by feeding them the input vector that caused the failure to begin with, and perhaps running some regression testing, some functionality testing, and see what happens to it, if there are any side effects. If we're happy, we can go ahead and deploy it, or we can wait for the administrator to click the deploy, or there are all sorts of strategies. But in principle, this whole thing can happen automatically. So the first case study is what we call the worm vaccine that targeted the problem of network worms using buffer overflow attacks. As I said, proof of concept, we don't really care much about buffer overflows, but they're a nice type of failure that people are interested in. And it has the other nice side effect that it's easily recognizable if you know what you're looking for. And also the network servers are transactional in nature, so we can easily replay input to them and see what the impact of that input is, right? So we're creating an easy system to test. So basically we take a production server, we instrument this server in a separate environment, whether it's a virtual machine or a completely different system, and we put some logic that does the identification of the fault and try to localize where the fault happened in terms of this routine. This is where it happened, right? This was the call trace, and create instances of this, test, and so on and so forth. And now we have several possibilities as to how we actually trigger this analysis. We can either wait for the attacker, I don't have a laser pointer, we can either wait for the attacker to directly attack the system. So this would be a honeypot-like version of the system, or we can put some type of anomaly detection at the end host or at the firewall, the router, that creates hints or suspicions that a particular request, a particular piece of traffic sequence of packets may be anomalous. We don't need to know for sure. We just need to create suspicions, right? And then we can test these suspicions in the analysis environment. So going from the simple block diagrams to once we fix it, we update the production server if we fix it, of course. And this is what the full architecture looks like. But moving on. So how do we create these sensors? How do we create this analysis environment? In this system, we use source-to-source code transformations excuse me? We use source-to-source code transformation to wrap all memory references, all accesses to buffers, that could potentially be susceptible to buffer overflow, and store enough information as the program runs to keep track of where it is executing at any given time. So when the program detects a buffer overflow, it emits all the information saying, hey, here's where I was executing, here's the buffer, here's the function, everything we need. And then we wait until an attack hits. One point here is that we can actually use any type of protection mechanism as an oracle, but we decided to use this approach because it's more efficient. So, the example that I gave earlier gets transformed to this example. It doesn't really matter. It just keeps track. The parts of the code in red is what the system injects. And basically, it uses a technique similar to electric fence to wrap buffers around memory protected with write protected memory pages that are zero fields. So overflows, underflows are going to create exceptions. Okay, 5 minutes. And so on and so forth. You can go through the slides later. Very simple technique. And the idea is that the same type of technique can be applied on the as a fix, in this case, where we save the state of the program right where it says set jump before the piece of code that we know is vulnerable, we detected in the past, string copy, and then if a fault does occur, we recover to it by skip execution. And in fact, in this case, the semantics are the same as if the programmer knew how to do array bounds checking. Oh. All right. So once we create such fixes, we test them with all sorts of bad input, good input, all the things, and then if we're happy, we can deploy. Does it work? Yep. We had 80-something percent success rate against known, well, to us, vulnerabilities against real open source software that we put in the system. We hit it with it, created patches that actually addressed the problem and kept the application running as well. And we could possibly do better. It took 60 seconds to do this for Apache, which is the biggest program that we had. I'll skip the performance because it works. Here's a system view of the web-based front end that can control the system. So we have a number of systems here, and we can launch an attack against them if we want. This shows what happens, the steps that the system goes through. Detect an attack, patch, generation, compile, test, pre-deploy. At pre-deploy, if the configuration may be that stay here until the administrator says go ahead and deploy. Of course, a patch may fail in the testing phase or the generation phase, and this is what the patch looks like because we operate in fully pre-processed source code. But if you look at the grayed out areas later on, I'll send the URL. You can see that the fixes are similar to what I posted earlier with the red lines on the code. And database of all sorts of failures. I'll skip the observations because they're fairly obvious. And now the problem with this is that it depends on the code that is compromised, that is wrapped around to not have any kind of failures, not have any kind of external memory references. So instead, we want to keep track of all memory references and do real recover, unroll as for the string copy or the piece of code that we've seen fail. And we'd like to operate in a binary-only environment, not require access to the source code as in this system. So we've built STEM, which stands for Selective Transactional Emulation, where we basically implement microspeculation and error virtualization by emulating just parts of a program as it's executing, and the rest of the program runs on the native CPU. And for the part of the program that's executing, you keep track of memory changes. And if anything bad happens, we unroll it and do error virtualization. Right. So otherwise, it's exactly the same technique as microspeculation, as I said. I'll skip the example in the interest of time. STEM semantics, performance, yada, yada. Performance, if you run the whole program under STEM, it's very, very slow. But if you run just a little bit of it, you may not even notice it, depending on what part of the code you're wrapping. For I/O-heavy programs, you could, in fact, run the whole program like SCP in the emulator, and you wouldn't see any performance degradation. But that's for a specific case of programs. And so the idea, I'll very quickly say, of application communities is rather than have a separate copy of the application that is instrumented and used as an analysis engine for those failures, since we're all running the same piece of software across 100,000 or 100 million different desktops, if some large subset of us is willing to collaborate, why can we not each take a little bit of the task of monitoring for failures in different parts of the code of the same program that we're all running, Word, and then when any one of us notices a failure, we just tell everybody, hey, here are the conditions that led to a fault, and now you can go ahead and create your own fixes potentially. So this is the notion of an application community. And in fact, you can think of it as load balancing the task of monitoring for failures using real applications rather than a honeypot or doing instrumentation around the application. Yada, yada. So there are all sorts of interesting questions in terms of what's the overhead of having an application community versus the speed of detection of a fault versus accuracy, who you trust, what types of fixes can be generated, so on and so forth. It's all very interesting. And if you want to hear about them, there are a bunch of papers. I'm going to send the URL that are appearing or are going to appear or have appeared that you can read, and you can feel free to send me email. And the top URL points to the project webpage. So that's all. Thank you.
All right, so let's thank our speaker.
Thank you.